morning. Inner product spaces. First, we need to know what an inner product is. U, V, W be vectors in a vector space V. Let C be any scalar. An inner product on V is a function that associates. Why did that A not show up? That's actually annoying. A real number with each pair of vectors u and v and satisfies the following axioms. This is the notation that I will be using. It's the notation I'm most used to. I think you may also see it with a comma instead of that vertical line, and I don't know how your textbook notates it. But that is how I learned it, that's how I'm most used to it, because that is the notation that we use in quantum mechanics. First, the inner product of u and v is equal to the inner product of v and u. So inner products are commutative. Second, the inner product of u with v plus w is the inner product of u with v plus the inner product of u with w. Third, c times the inner product of u with v equals the inner product of cu with v. And again, keep in mind that all of these operations, the plus and the multiplication, are defined in v. It's addition as defined in v and multiplication as defined in v. And finally, the inner product of v with itself is greater than or equal to 0. It's non-negative. And it equals 0 if and only if v is the additive identity. And v is your 0 vector. This is an inner product. And this is the final operation that we'll be studying in inner products. An inner product space is simply a vector space with an inner product. Is there anyone who has not had either Calc 3 or Intro Mechanics? Oh dear. Now, for the rest of you, you're already familiar with one inner product. Consider Rn. Your standard inner product is the dot product. Right, for those three of you who have not had either mechanics or Calc 3, we'll be looking at the dot product shortly. But it's really simple. And so consider three vectors in an inner product space V, U, V, and W. Let's see the real number. The inner product of 0 with V is the same as the inner product of V with 0, which is obvious because it's commutative, and that is equal to 0. Sometimes you'll see the third axiom. Second axiom. Sometimes you'll see the second axiom as this property, right? So they flip the property in the second axiom. The inner product of U plus V with W is the inner product of U with W plus the inner product of V with W. The inner product of U with CV is C times the inner product of U with V. Well, if you take that third property there, along with our third axiom, together what they say is where you put the scalar doesn't matter. Right? You can either do the inner product first and then multiply by the scalar, or you can multiply U by the scalar first and then take the inner product, or you can multiply V by the scalar first and then take the inner product. We're going to get some new measures with inner products. Let U and V be vectors in an inner product space. The norm of U is the square root of the inner product of U with itself. Right? You'll see norm is represented with double vertical lines. Those are called the norm bars. I stick with the terminology norm. You may also see it referred to as length. It's just if you're dealing with matrices, it doesn't make sense to define length of a matrix. And so I'll stick with norm. Distance between U and V is the norm of U minus V. Angle between two non-zero vectors U and V, given by the relation cosine of theta, is the inner product of U with V over the norm of U times norm of V. And theta will always be restricted to 0 pi. Finally, we say that two vectors u and v are orthogonal if the inner product of them is 0. This terminology orthogonal may not be used in mechanics, but it is used in Calc 3. So my Calc 3 keeps. What does orthogonal mean if we're dealing with just standard vectors?
Perpendicular.
Perpendicular. Just a fancy way of saying perpendicular. There's actually a third way of saying that too. Again, Calc 3 keeps should know this. Normal. So if you say two planes are normal to each other, that means they intersect at a 90-degree angle. They're perpendicular. I have only one term when you can have three. That means the exact same thing. Cauchy-Schwarz inequality. U and V be vectors in an inner product space V. Then the absolute value of the inner product of U with V is less than or equal to the norm of U times the norm of V. Great exam question. It's a shame how we wrote your exam. I don't feel like going back and changing it. Triangle inequality. U and V be vectors in an inner product space, then norm of U plus V is less than or equal to norm of U plus norm of V. Thought quick enough, this would make a great exam question. Prove the triangle inequality. Oh well. Otherwise, you should already be familiar with the triangle inequality, but with real numbers instead. For all real numbers, x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. We're now extending that to the more general vector. Here's another theorem that should be familiar. Pythagorean theorem. Let U and V be vectors in an inner product space V. Then U and V are orthogonal if and only if the norm of U plus V squared equals the norm of U squared plus the norm of V squared. Let U and V be vectors in an inner product space V such that V is not the zero vector. The orthogonal projection of U onto V is defined as the inner product of U with V divided by the inner product of V with V times V. Again, remember, all of these operations are defined in your vector space, or as defined in the vector space. So we have vectors in R3. So let's start. By finding U dot V. U dot V, this is the dot product, which is the standard inner product for Rn. Write that down. Standard inner product in Rn is the dot product. Very simple. Multiply corresponding components and add them together. So U dot V, 1 times 2, plus 2 times negative 3, plus 4 times 5. Two minus 6, negative 4, plus 20. That's your dot product. And that's all there is. Some of you, this may be flashbacks to the prelude of your nightmare that was chapter 3. This is what, day 3 of Cal 3 for us. And this is the third thing we did in Cal 3, right? We did the, it's the introductions, then we introduced vectors, and then this is the dot product. And so this was day 3. Back when we thought Cal 3 being easy day.
So which one should we take first?
Doesn't matter. You can actually take linear and Cal 3 together. I think that's generally what they recommend we do.
The first test of almost every one I wrote.
Next up, let's look at U dot W. One times 4 plus 2 times 2 plus 4 times -3. 4 and 4 is 8. 8 and -12. -4. There's the dot product. Easier than eigenvalues were. V dot W. 2 times 4 plus -3 times 2. Plus 5 times -3. 8 minus 6, 2, 2 minus 15, -15. U plus V dot with W. By our second property, U dot W plus V dot W. What did you say U dot W was?
-4.
And what was V dot W? There's U plus V dot W. I'll let you do U plus V first and then dot W and verify you get -17. Norm of U By definition of norm, the square root of u dot itself. Square root of 1 times 1 plus 2 times 2 plus 4 times 4. One and 4 is 5. 5 and 16. Square root of 21. Finally, norm of v. Again, by definition, that's going to be the square root of v dot v. Square root of 2 times 2 plus negative 3 times negative 3 plus 5 times 5. 4, 9, 13, 13 and 25. 38. Can that be simplified? Not be simplified. No. 38 is 2 times 19, neither of which are perfect squares. So there we go. Obviously, root 21 couldn't be simplified either, right? That's 3 by 7. Again, neither of which is a perfect square. We go on the dot product. Good. Dot product's boring now. We're going to verify that is we're going to prove that this defines an inner product in R2. So given here is 2 vectors, 2 arbitrary vectors in R2. Oh, we actually need a W too. let u, v, and w be three arbitrary vectors in R2. And let C be a real number. Remember, in order for this to be an inner product, it must satisfy those four axioms. So first, look at the inner product of u with v. We have to show that that's going to be the inner product of v with u. Well, that's the definition of the inner product, right? But u1 and v1, aren't they just real numbers? If you take the product of real numbers, it's commutative, right? If you take the product of real numbers, it's still a real number, right? And addition in real numbers is commutative. So can't we write that? But now, isn't that the definition? Of the inner product, v with u? First axiom is satisfied. U with v plus w. Since we're dealing with R2, standard addition. All right, so v plus w would be v1 plus w1, v2 plus w2, right? we're dealing strictly with real numbers. And real numbers distribute. So distribute everything through. But again, we're dealing with real numbers. Products of real numbers are real numbers. Addition in real numbers is both commutative and associative, right? So the order we write addition doesn't matter, and our grouping doesn't matter. We would be able to write that, wouldn't we? Right, group all the U and V's together, group all the U and W's together. But what does that first grouping look like?
First axiom,
What do you mean first axiom?
like the one we just did.
So it's the inner product of U and V.
Yeah.
What about that second grouping? Isn't that just the inner product of U with W? Oh, that's what we wanted. Second axiom has now been established. The third axiom. C times the inner product of U with V. That's going to be what? C times U1, V1 minus U2, V2 minus U2, V1 plus 3 U2, V2. That C can distribute, right? Because we're dealing with real numbers. Technically, I should write this. But everything's a real number. Multiplication of real numbers, commutative and associative. Order doesn't matter, grouping doesn't matter. We would group it like that, right? Now C times U, since we're dealing with R2, that would just be the vector CU1, CU2, right? So then wouldn't that just be the inner product of C times U with V? Oh, that should be, sorry, that last there, that should be just a 2 there. Third axiom has now been established. Final axiom. Take the inner product of U with itself. But U1 times U1, just U1 squared, right? U1 times U2, U2 times U1, they're the same. Minus 2U1, U2, and then plus 3 U2 squared. How can we show that's greater than equal to 0?
Could you show me what axiom again? I just want to make sure my notes are there.
PowerPoint doesn't seem to work. Hold on a second, you can restart PowerPoint, because something seems to be off. my notes, I can't go off my notes. Right, that will show that it equals 0 if only if D is the 0 vector. That's not hard to do. I'm first trying to show that the inner product just calculated always has to be non-negative. Not quite sure how to do that. I'm going to have to get back to you on that one. Assume what I'm going to have to do is probably a proof by contradiction. Assume that that's less than 0. Somehow. Yeah, I'm not going to waste too much time. It is true. I'm just not quite sure how to go about showing it right now. To be continued, I'll examine that. Consider these polynomials in P2. With the inner product, oh, look at that. With the inner product defined as the inner product of f with g is the integral from 0 to 1 of f of t times g of t dt. We're going to evaluate the inner product of f with g, the inner product of f with h, the norm of f, and the norm of g, and then we'll normalize f and g. Let's start with inner product f with g. 0, 1. T plus 2 times 3t minus 2 dt. Integral from 0 to 1. 3t squared plus 4t minus 4. How do we find integrals? So what would it be?
T cubed plus 2t squared minus 4t. And then evaluate that along with the
So what did you use? What's that called?
Antiderivative?
So power will find the antiderivatives, but then you said to evaluate it. What is that called? Fundamental theorem of calculus, which part? Part 2. All right, fundamental theorem of calculus, find an antiderivative. Say that big F is your antiderivative. Then it would be big F of 1 minus big F of 0. All right, there's our simple antiderivative. And it's 1, so that makes it really nice. And the other one's 0, which makes it really nice. 1 plus 2 is 3, minus 4. It's negative 1. Now f with h, integral 0 to 1. T plus 2, t squared minus 2t minus 3 dt. Do that distribution. T cubed minus 2t plus, minus 2t squared plus 2t squared is 0, that's nice. Minus 3t minus 2t, minus 4t would be minus 7t. Then we get what, minus 6? What would our antiderivative be?
T to the fourth over 4 minus 7t squared over 2 minus 6t.
Drag that from t equals 0 to 1. Again, that is a really nice interval to evaluate over. A quarter minus 7 halves minus 6. So we want 1 minus 14, negative 13, minus 24, negative 37. Don't you wish you'd go back to doing this again? Go back to Calc 1 all day, every day? Norm of F. Square root of the integral from 0, 1. Of f of t times f of t, dt. Don't even need to evaluate. Don't even need to expand that. U sub. Let u be t plus 2. What's du? U is t plus 2. What is du? Not just one. Not du, dt. Du is dt. That's nice. T plus 2 cubed over 3 would be your antiderivative. At 1, you get 1/3. I'm sorry, not 1/3. At 1, you get 9. Right, 3 cubed over 3, 3 squared, 9. At 0, you get 8/3. So what's 9 minus 8/3? 27. Yeah, 27 minus 8. 19. 19/3. Which does not simplify. So norm is square root of 19/3. Norm of G. Square root of the integral from 0 to 1 of G times G dt. Again, we can use u sub. U is 3t minus 2. That means du is 3 dt. Square root of 1/3 times 3t minus 2 cubed over 3 from 0 to 1. 3 minus 2 is 1. So at 1 you get a 9. At 0, be 8 9ths, right? One ninth minus 8 ninths is negative. Something's wrong. Oh, I'm sorry. No. It's negative 8 ninths. It's negative 2 cubed. Ninth minus negative 8 ninths is positive 1. And the square root of 1 is 1. That's nice. G has a norm of 1. We call G a unit vector then. Unit vector is any vector of length 1, or of norm 1. Normalize f and g is just that. Make it have a norm of 1. All right, we typically would represent that e sub f. One over the norm of f times f. And I don't feel like distributing that through. E of g is already a unit. Or g is already a unit, so e sub g would just be g. Let's do this one. Find cosine of theta between u and v in R4 with standard inner product. So remember that means cosine of theta u dot v over norm of u times norm of v. U dot v, 2 minus 9 minus 20 plus 4, right? Over the square root of u dot u. 1 plus 9 is 10. Plus 25 is 35, plus 16, 51. Four and 9 is 13, 13 and 16 is 29, and 1 is 30. What's 6 minus 29? Negative 23? Oh, this is going to be fun. What is 51 times 30? I don't need a calculator.
1,530.
I have no idea if that's right. Let's do 51 times 3 first. 150 and 3 is 153, right? Times that by 10. Yeah. 1530. So you're right. Can that be simplified? Yes. 1 plus 5 is 6, plus 3 is 9, it's divisible by 9, which is a perfect square. What's 1530 divided by 9? What's 153 divided by 9? You cheat. And then multiply it by 10. And that is not divisible by 9. That is not divisible by 10. I'm sorry, why would I say 10? It's not divisible by 100, which would make square root of 10. I don't think that's divisible by a perfect square, so you're done. There's your cosine of theta.
Can we leave it as radical 1530?
I just plug that into your calculator and try and simplify it.
There.
Because your calculator will simplify that for you. So I'd say no. Type into your calculator and just write out what it simplifies to. I'm going to let you do that one. We want to find the value of k so that these two vectors in R4 with standard inner product are orthogonal. Remember, orthogonal means that their inner product is 0. Three plus 2k plus 7k minus 15. 9k minus 12 has to be 0. Solve for k. K would have to be 4/3, right? There you go. And like I said, I'll put that one back on the screen. Do that one on your own. And so it's kind of like, it's actually exactly what we just did, it's just a different vector space with different inner product. Right, so it's different inner product space, otherwise it's the same. So we have 2 possibilities for next week. I could cover the last topic, which is orthogonalization, finding orthogonal bases using the Gram-Schmidt process on Tuesday, and then have Thursday be if you have any questions before the final. Or I would give you Tuesday to work on the project that's due next Thursday, and then do the Gram-Schmidt process on Thursday. Which would you prefer?
The second option.
So let's go by a show of hands. Who wants to have Tuesday to be to work on the project? 5, 6, that one just went out. So that's what we're going to do. Tuesday's going to be work on the project. I would come into this room. I will sit here for Tuesday. If you want to come and work on the project in class and ask questions. Otherwise, you don't have to show up if you want to work on the project outside class. And then Thursday, we do the Gram-Schmidt process. Have a good weekend.